Our next segment on fluid statics is on how to find the density of an object. And in this particular example, we have an object hanging from a scale and we're measuring the weight, and the weight in air is 40 newtons. And then we weigh it again when the object is submerged in water. So let's assume that this is in water, H2O. And then the weight is only, let's see, I didn't write it down. Let's say it's 32 newtons. That's a terrible looking N. So let's write that again. 32 newtons is the weight when it's submerged in water. And of course, sometimes that's also called the parent weight of the object. And so we're going to use what we call Archimedes' principle. That's named after the famous Greek scientist, I guess we could call a mathematician scientist, who discovered how to find the density of objects by realizing that when you submerge an object in water, it displaces an equal volume of liquid. And from that, he was able to find the volume of a very strange shaped object. And from that, he could figure out the density of the object, because in order to find the density, you have to know the volume. You can always measure the mass on a scale, but how do you measure the volume of an object that is very oddly shaped? And so by submerging it and finding out how big the volume of the displaced liquid is, you can then find out the volume of the object. So that's what we're going to do here indirectly. So again, to find the density of an object, we need to know its mass, and then we divide it by its volume. But how do we find the volume? Well, a little trick here. Why does it weigh 40 newtons in the air and 32 newtons when it's submerged in water? Because inside the liquid, it experiences what we call the buoyancy force. And the buoyancy force is equal to the difference in the weight as it's measured in the air to the weight that it's measured as it's submerged in the water, because the buoyancy force pushes back with a force of 8 newtons, so therefore something that would normally weigh 40 newtons now only weighs 32 newtons. So in this case, the buoyancy force is equal to the weight in air minus the weight in water. So in this case, that's equal to 40 newtons minus 32 newtons, which is equal to 8 newtons. And then we've also learned in the previous segment that the buoyancy force is equal to the weight of the displaced liquid. And of course, the equation for weight is W, and W is equal to the mass times acceleration due to gravity. So the buoyancy force is equal to mg. And then we can replace the m by using the definition of density. We can say that the mass is equal to the density times the volume. And so over here, we can say that the buoyancy force is equal to the density times the volume times g. Now, this is the density of the liquid, and this is the volume of the displaced liquid, which is also the volume of the object. And so if we can solve this for the volume of the displaced liquid, we can then also say that is equal to the volume of the object. So in this case, we can say that the volume is equal to the buoyancy force divided by the density and acceleration due to gravity. And remember, the density is the density of the displaced liquid. Since we know the buoyancy force, which is 8 newtons, and the density of the liquid, which is water, which is 1,000 kilograms per cubic meter. And then, of course, we know g, which is 9.8 meters per second squared. We can now calculate the volume of that object. So 8 divided by 1,000 divided by 9.8 is equal to 8.16 times 10 to the minus 4. And of course, the standard unit for volume is cubic meters. So it's a small object. Now we can go ahead and measure or calculate the density, because it says here that the density is equal to the mass divided by the volume, and the volume we now have. But what about the mass? We didn't measure the mass, we measured the weight. And of course, we know that the weight is equal to the mass times g. That means that the mass is equal to the weight divided by g. So we take the weight divided by g, and that gives us the mass of the object, and that's what we plug in here. So this is equal to the weight divided by g, and then we divide that by the volume that we just found. So this is equal to 40 newtons divided by 9.8 meters per second squared, and take the whole thing and divide it by the 8.16 times 10 to the minus 4 meters cubed. So the mass divided by the volume gives us the density. So we take the inverse of that, multiply it times 40, and divide it by 9.8, and that gives us 5,000. So this is 5,000 kilograms per cubic meter, and that is the volume that we were looking for, the volume of the object. So notice that that is 5 times the density of water. Now this is just a hypothetical question. I don't know if there's any object here that has a density of 5,000 kilograms per cubic meter, but that's the correct answer for this particular problem. Oh, thank you. Yes. Oh, it's not the volume, it's the density that we're looking for.